let's work a few problems from the book dealing with inner products and norm spaces. So here, first we're just going to work with some norms. We're going to take these three vectors that exist in R3, and we're going to compute the norm of these vectors for three different norms. So we're going to work with the 1 norm, the 2 norm, and the infinity norm. This is a relatively straightforward problem, but let's just kind of work our way through it. So taking the vector -3, 4, 0, transpose, I guess, and we want to find the 1 norm of that. Remember, our definition for the 1 norm said that we take the absolute value of our first component plus the absolute value of our second component plus the absolute value of our third component. So we have 3 plus 4 plus 0. And we get 7. Not too bad. Our 2 norm of the same vector. Well, our 2 norm is the one that we're most familiar with. This is the one where we have the square root. We're going to take the square root of -3 squared plus 4 squared plus 0 squared. So 9 plus 16, we're going to get the square root of 25, and we ultimately get 5. Finally, our infinity norm. Remember, this is the one that we take the maximum of the absolute values of each of our components, which I'm just going to list out in braces. So which one of these is biggest? Well, we're dealing with a 3, a 4, and a 0. The biggest of those is 4. And that's all there is to calculating these three norms for this vector. And we'll just go ahead and repeat that for the other two vectors. What's the 1 norm of -1, -1, 2? Again, just sum the absolute values. We have 1 plus 1 plus 2, and we get 4. Then we want the 2 norm. And again, taking the square root of -1 squared plus -1 squared plus 2 squared. Technically, from our p-norm definition, all these would be absolute values of something squared. We don't need the absolute values because the square takes care of that for us. But here we have the square root of 1 plus 1 plus 4. So we end up with the square root of 6, and in this case we can't simplify that. Then we have the infinity norm of -1, -1, 2. And that should be an infinity, not a 2. And again, this is the maximum of the absolute values of -1, -1, and 2. So we're dealing with 1, 1, and 2. The biggest of those is 2. And finally, we do the same thing, but for the vector 1, 1, 1. So, absolute value of 1. So I'll go ahead and keep writing the absolute values in here, even though we don't really need them for this one. 1 plus 1 plus 1 is 3. Shouldn't be too hard to see that one. Then we have the square root of 1 squared plus 1 squared plus 1 squared. That's now the square root of 3. And then finally, the maximum. I'll go ahead and keep writing the absolute values, and that should not be a plus. So maximum of 1, 1, and 1, they're all 1s. Okay. But these norms are really easy to compute. Actually, the hardest one to compute of these is the 2 norm, but the 2 norm has certain properties that make it the most useful one of the lot. So, but the 1 norm and infinity norm are very commonly talked about just because of the ease of the formulas, how easy they are actually to work with, even if they don't actually come from an inner product. Next, we're going to work problem 20. Here we start with a square n by n matrix that is non-singular, and for every vector in Rn, we're going to define the you could say the A norm. Let's just call it the A norm for short. The A norm will be the 2 norm, so this is the regular 2 norm of A times x. So x is a n by 1 vector. When you multiply by an n by n matrix, you're going to get another n by 1 vector. And we're going to take the 2 norm of that result and call it the A norm of the original vector. And we're going to show that this actually does define a norm on Rn. So this is actually an A norm. That terminology is actually correct. So we have 3 properties to show. Well, first things first, property 1 is actually a 2-parter. First thing, we want to show that the A norm, we want to show that this is always non-negative. But since it's defined in terms of the 2 norm, and this thing only ever spits out non-negative numbers, then it's definitely always going to be non-negative. So that part is really easy. But what about if we have that A norm equals 0? How can we show that means that x has to be the 0 vector? Well, if the A norm is 0, that means that the 2 norm of A times x is 0. But the 2 norm is a norm. If the 2 norm of something equals 0, that something has to be 0, the 0 vector. So A times x has to be the 0 vector. And here is where we're going to use the fact that A is non-singular. Since A is non-singular, the only vector we can multiply A by to get the 0 vector is the 0 vector. So the only vector whose A norm is equal to 0 is the 0 vector. And that's what we wanted. And obviously we can go the other way. We need, when x equals 0, the A norm to be equal to 0. But if x is 0, then A times x is 0, and so the 2 norm of A times x is 0. It's usually this direction that's the hardest thing to prove. What about the A norm of a scalar times x? Can we pull that scalar out? Well, again, we go back to our definition. Our definition is that we're going to have the 2 norm of A times the vector that we have in here, which is alpha times x. Well, A times alpha times x, we can pull that scalar out into the front. So this is alpha times ax. But now, because we're working in the 2 norm, we're allowed to pull that alpha outside. And again, it becomes an absolute value of alpha on the outside. And so, using our definition again for what the A norm is, this is the A norm of x. So we have the absolute value of alpha times the A norm of x. Okay? So we're able to pull that alpha outside. Finally, we need the triangle inequality. This time, the triangle inequality is not going to be as painful. So we're looking at the A norm of A plus y. This is going to be the 2 norm of A times x plus y. I think I said this was A plus y. This is x plus y. Once we do that, well, we also know that we have a matrix times a sum. We can distribute that. We have A times x plus a times y inside of our 2 norm. And then this thing is the sum of two vectors in a 2 norm. We can use the triangle inequality for the 2 norm to say that this thing is less than or equal to the 2 norm of ax plus the a norm of, or the 2 norm of ay. And of course, the a norm of ax is the a norm of x. The 2 norm of ay is the a norm of a norm of y. So this is a norm of x plus a norm of y. And so this a norm of a sum is less than or equal to the sum of the a norms of x and y. And that's all we need to show. But we did need to have A be a non-singular matrix for this to work. Now let's actually work with something that's not in Rn. So here we're dealing with C of 0, 1. So continuous functions on the interval from 0 to 1. And we're going to use the inner product they say defined by 3. That means that our inner product here, if we're taking two functions, the inner product of those two is going to be the integral from 0 to 1 of f of x times g of x. What are we going to do here? We're going to take two vectors here being functions, and they're going to be the vectors 1 and x. So f of x equals 1 and g of x equals x. Could say. We're going to first find the angle between those two functions, those two vectors. What does that mean? Well, it's the exact same process of what we did before. We need to find the inner product of 1 and x. We need to find the norm of 1. And we need to find the norm of x using this formula that we have up here. So let's just start with the inner product of 1 and x. This is going to be the integral from 0 to 1. First function is 1, so the f of x is 1. Second function is x. And we're literally just taking the integral of x from 0 to 1. Integral of x is 1/2 x squared. Hopefully you guys remember that. If we take that from 0 to 1, we plug in 1 first, we get a 1/2. Then we plug in 0, we get a 0. 1/2 minus 0 is a 1/2. What about the norm of 1? Now, technically, we're talking about a square root of an inner product. So to not mess with the square roots, I'm going to first just go ahead and square that. We're going to square these norms, so we don't have to worry about the square root until after we've done all of our integration. So now this is the inner product of 1 with itself. So we're literally just putting 1 in for f, 1 in for g. We have 1 here, 1 here. What is the integral of 1? Well, it's just x. Evaluated from 0 to 1, which means we plug in 1, we get 1. We plug in 0, get 0. 1 minus 0 is a 1. Or in other words, the norm of 1, if we take the square root of that, we get 1. Then we do the same thing for x. Remember, this time both f and g are x. So we're taking x times x. Or in other words, we're integrating x squared. The integral of x squared is 1/3 x cubed. Again, going from 0 to 1. We plug in 1, we get 1/3 minus 0. So we have 1/3 here. This time, taking the square root does matter. We get a 1 over the square root of 3. We could rationalize that, but it'll turn out to be easier if we don't do that. Because what are we going to do now? We're going to go ahead and put these numbers that we derived into a formula. The formula being that the cosine of theta is the inner product of 1 and x over the product of the norms of 1 and x. So put 1/2 on top. we have 1 times 1 over root 3. If we go ahead and move stuff around, so the 1 over root 3, we can flip it upside down and put it on top. Get a square root of 3 on top. The 1/2, well, the 2 ends up on the bottom. The 1 obviously doesn't really matter. It kind of just gets absorbed into everything else. So we get that the cosine of theta is root 3 over 2. So now we actually have to think about what theta gives a cosine of root 3 over 2. And specifically, we're only looking at angles between 0 and 180 or 0 and pi, depending on which one you want to use. And I'm not going to be too picky about that. So the only angle between 0 and pi that gives you a cosine of root 3 over 2 is pi over 6. Or, if we're using degrees, we can say it's 30 degrees. So that's the angle between 1 and x in this vector space. If we use a different inner product, we'd get a different result. But this is the one that we got for this inner product on this vector space. All right. Now we're going to find the vector projection P of 1 onto x. And then we're going to verify that 1 minus p and p are orthogonal. I'm going to do that on another page. So we're projecting 1 onto x. Now what is our formula? Remember, we have a formula for this. The projection of u onto v is the inner product of u and v over the inner product of v with v, or you could say the magnitude of v squared, or the norm of v squared, times the vector v. Remember, this is just a scalar overall times the vector v. Here the u is equal to 1. Just say this is part b. And our v is equal to x. And we're going to actually use the same numbers that we got from part A. So here our p, the inner product of 1 and x, over the inner product of x with x, but that's just the norm of x squared. And then our vector v is just x. We saw that the inner product of 1 and x was 1/2. Our norm of x was 1 over the root 3, but since we're squaring it, it's just going to be 1 over 3. And then we multiply that to x. Of course, we can go ahead and simplify that. 1/2 divided by 1/3 is 3/2. So that's our projection. Our projection onto x of 1 is 3/2 of x. Of course, then we can say 1 minus p is equal to 1 minus 3/2 of x. We can't really simplify that. That's just what it is. But we do want to show that these two vectors are orthogonal to each other. How do we do that? Well, we just want to show their inner product is 0. So what is the inner product of this vector p with this vector 1 minus p? Or in other words, what's the inner product of 3/2 x with 1 minus 3/2 x? Well, our formula says that we're just taking the integral from 0 to 1 of the product of these two functions. So we have 3/2 x times 1 minus 3/2 x. And then dx. Of course, we're going to have to do a little bit more computation this time. I'm going to go ahead and pull out the 3/2 and then distribute the x to the other term. So we have x minus 3/2 x squared. If we integrate that, we have a 3/2 times, well, integral of x is 1/2 x squared. Integral of x squared is 1/3 x cubed, so we'll have an x cubed here, but 1/3 times 3/2 just leaves us with a 1/2. That's going to be evaluated from 0 to 1. So we'll have 3/2. We plug in 1, so we get a 1/2 minus 1/2. We plug in 0, we get 0 and 0, so we just have the 1/2 minus 1/2 in here. Of course, that equals 0. The 3/2 didn't really contribute there, but we get a 0 overall. these two vectors, p and 1 minus p, are orthogonal to each other. Finally, on part C, we're going to go ahead and compute the norm of 1 minus p, p, and we already have 1. Remember that is just 1. And we're going to verify the Pythagorean law for that. So we'll do that on this page, remembering that p is 3/2 x, 1 minus p is 1 minus 3/2 x, and I guess we'll go ahead and write this, even though it shouldn't be too hard to remember that one. Okay, what is the norm of p? Well, norm of p is the norm of 3/2 x, and I'm just going to go ahead and use the property of the norm that we know, that if we have a scalar times a scalar times a vector, we can pull that scalar out, or with the absolute value if we need to, but in this case we don't need to. We just have 3/2 times the norm of x, and we know the norm of x to be 1 over the root 3. We already figured that one out, so it will save ourselves a little bit of work here. So we have a root 3 on the bottom, which we can actually rationalize this. 3 over root 3 is just root 3, so the norm of p is just root 3 over 2. That's the easier one. The other one we're not going to be able to do the same kind of trick with. I'm going to go ahead and square this because we are going to have to use our integral definition. We're taking the norm of 1 minus 3/2 x, and we're going to have to use our integral formula for that. So the integral from 0 to 1 of this vector with itself, which is just that squared. We'll go ahead and expand it so we can actually do the integration. So we have 1 minus 2 times 1 times 3/2 x, so we actually get a minus 3x. And we get a plus 9/4 x squared. Take the integral. Integral of 1 is x. Integral of 3x is going to be 3/2 x squared. And then integral of 9/4 x squared will be, well, we're going to get an x cubed here. We're going to get a 3 on the bottom. The 3 on the bottom will cancel one of the 3's on top, so we'll get a 3/4 x cubed. That's going to be evaluated from 0 to 1. Of course, the 0 on the bottom is going to make everything 0. Really what we're doing is plugging in 1. We have 1 minus 3/2 plus 3/4, and that's ultimately going to be 1/4. Or in other words, because we squared this to begin with, the norm of 1 minus p is actually 1/2. Alright. Therefore, what do we want? Well, we want the norm of 1 minus p squared plus the norm of p squared. We want that to equal the norm of their sum, because we said that 1 minus p and, well, not said, we showed that 1 minus p and p are orthogonal to each other. So the Pythagorean law says that the sum of their squares should equal the square of their sum. So what is this equal to? Well, we have norm of 1 minus p squared, so we have a 1/2 squared. We have a root 3 over 2 squared, which is a 1/4 plus 3/4, which is equal to 1. And we're saying, is that the norm of their sum? Well, their sum, the sum of 1 minus p and p, is literally 1. So is this the square of the norm of 1? Well, yeah. Norm of 1 is 1. Square of that is still 1. So that's the norm of 1 squared. So the Pythagorean law does work, as it should, but we're just verified it in this particular case. Finally, let's look at problem 9. Here we're going to again look at our same kind of idea with our continuous functions on an interval. our our vector space here is going to be continuous functions on negative pi to pi, and we're going to have an inner product defined by an integral. Now, they define it a little bit differently. We're putting on a weight here. The weight is actually to make certain things come out to be unit vectors that otherwise wouldn't be. Basically, everything's just going to be scaled by 1 over pi to kind of deal with the fact that we have pi's in our formula here. So our formula for our inner product of f and g is 1 over pi times the integral from negative pi to pi of f of x times g of x dx. We want to look at the functions cosine of mx and sine of nx. Here m and n might be the same or they might be different. We're not really told. Technically here, a lot of times what people do for this particular inner product space is that they actually allowed us to work with all the m's and all the n's and have a whole bunch of vectors that are defined as cosines and sines. We want to show that these two vectors for a fixed m and a fixed n are always going to be orthogonal to each other and are always unit vectors. Hence the 1 over pi is here to make sure those are unit vectors instead of having pi's pop up in our formulas. So we need to show they're orthogonal. That's our first priority. How do we show things are orthogonal? We show that the inner product is equal to 0. So what is the inner product of cosine of mx and sine of nx? And we get to put that into our formula. We have 1 over pi, integral from negative pi to pi. We have cosine of mx, a sine of nx. And we get a integral that on the face of it looks really complicated to solve. Now technically we could actually do this one. It is possible to integrate that directly. We'd use something called the product of sum identities. So sine times cosine with different insides, a u and a v, is actually equal to half of the sum of sine of sine of u plus v plus sine of u minus v. And we could split it up that way. But we don't actually need to do that here. In fact, I'm just going to go ahead and get rid of this because we do not need it. What we're going to do is recognize that cosine is an even function. If we put negatives in here, the negatives just disappear. If we plug negatives into sine, the negatives can be pulled out. Sine is an odd function. And so if we plug a negative into this product, we have one negative coming from the sine, no negatives coming from the cosine, and we can pull that negative out. This product is an odd function. And one of the results that you may remember from Calc 1 is that if you integrate an odd function on an interval where it goes from negative a to a, in this case our a is pi, we always get 0 every single time. Because if we were to draw out the functions, on one side where it's positive, it's negative on the other side. If on the other side of 0. And so we'll always have parts that cancel each other out on both sides. So let's say our integrand is odd. So kind of cheated the system there a little bit, but save ourselves some time. Don't want to spend forever on this problem. And that's the kind of thing that we want to be able to do to actually do mathematics right. Alright, so they're orthogonal to each other, regardless of what m and n are. Why are they unit vectors? Well, there we're going to have to compute their norms. And of course, I'm going to go ahead and take the norms squared, so I don't have to deal with square roots for the moment. And this is going to be the inner product of cosine of mx with cosine of mx. So I have a 1 over pi. I have the integral from negative pi to pi And now, because these are both cosine of mx, I get cosine squared of mx. And here's where we actually had to do some work. So, if you remember, how do we integrate a cosine squared? We use an identity. In this case, so let me put it over here. Cosine squared of, let's do theta, is equal to 1/2 1 plus cosine of 2 theta. That's our power reduction formula, I think we called it. So we're going to have a 1/2. I'm just going to pull the 1/2 out of the integral, so we have 1 over 2 pi out in front instead of 1 over pi. Still integrating it from negative pi to pi, but now we're integrating 1 plus cosine of 2 times what we originally had in here. So instead of theta, we had mx, so we'll have a 2mx. Okay, we integrate that. Integral of 1 is x. Integral of the cosine. We have cosine of something times x. That something just ends up being a 1 over that something on the outside. Integral of cosine is a positive sign, so we didn't actually change that. And we still have the 2m times x on the inside. Okay. Now what do we get when we put pi's in here? Well, when we first put pi in, we get a pi here. Then what happens here? Now, here's where the wording of the problem is a little bit insufficient. They didn't state it in the problem, but they are assuming here that m and n are integers. This doesn't work if they're not integers. So if m is an integer, then we're working with a sign of an integer times pi. Sine of any integer times pi, so sine of 0, sine of pi, sine of negative pi, sine of 2 pi, all of those are equal to 0. So that part is gone. We don't have to worry about it. So this is pi plus 0. Let's go ahead and put that in. Now we subtract what we get when we plug in negative pi. Well, negative pi in here is a negative pi. Then, I guess, minus, because we have to distribute that negative. But it won't really matter because now we're still dealing with some integer times pi. This just, in this case, it's going to be a negative integer. But the negative doesn't really matter too much. So we still get 0. So what do we have here? We have zeros that go away. We have a pi and then plus pi. So inside here we get a 2 pi. 2 pi over 2 pi is 1. Or in other words, because we squared it in the first place, not that it's going to really change too much, take the square root, and we get the norm of cosine of mx is equal to 1. Alright. Now we get to do the same thing for sine. But we'll see that we can keep some of this work and actually use it in the next part. So here I've gone ahead and copied what we did for cosine, and we're going to make the changes that we need. So we're going to change this to a sine. I'll go ahead and change this to a sine. And then we need to know how we integrate sine squared. Well, our formula this time is very similar. Sine squared of theta is 1/2 of 1 not plus, but minus cosine of 2 pi. Or, sorry, cosine of 2 theta. So where we had a plus before, now we have a negative. Where we had a plus here becomes a negative. But it doesn't change how we integrated the 1 or the cosine of 2mx. We get the same result, but just with a sign change. Technically, that will change the sign here, and then we'll make this one a plus sign. So we have a plus, but we're changing the signs on zeros. So it actually doesn't change anything about the computation. We still get a 1 at the end. So we get to save ourselves a lot of work since we know the other formula is very similar to what we had before. Just changing a few signs in here, we get the same result. This one is also a unit vector. Now what do we have left? They want us to also determine the distance between the two vectors. And technically what that means is that we're taking, I guess probably should change all the m's in here to n's. So let me do that. All right, so we're working with sine of nx and not sine of mx, but it doesn't really change the process. But we're taking the norm of the difference of cosine of mx and sine of nx. And that's what they're asking for. Now, if we were to do this directly, we'd have to do another integral. And we might have some mixed terms in there. Might actually be a little bit more work than we did before. So let's do it the easy way and realize that we're working with a sum or difference. We're working with a difference here, but we might as well be working with a sum of two things that are orthogonal. Negative sine of nx is orthogonal to cosine of mx. So what does that mean? It means we have the Pythagorean law. If we square this, this is equal to the norm of cosine of mx squared plus the norm technically of negative sine of nx, but the norm gets rid of any negatives anyways, so I'm just going to write this as norm of sine of nx squared. So Pythagorean law works even if you're doing a difference instead of a sum. Same kind of formula. Well, what's the norm of cosine of mx? It's a unit vector. We know that's equal to 1. Technically 1 squared, but still 1. Same thing with sine of nx. It's unit. This is 1. We're adding a 1 here. 1 plus 1 is 2. Hopefully I shouldn't have to explain that one. And so that means that the norm, because remember we had to put the square there to make this work out nicely, we're going to have to take the square root, so we get square root of 2. Very easy once we know those are orthogonal vectors. And one of the reasons why we like having orthogonal vectors so much. Alright, so I'm going to leave that there. Next class we will talk about some other reasons why we love orthogonal vectors as we talk about orthonormal sets and orthonormal bases. Because it turns out that if we can have a basis where all vectors are orthogonal to all the other ones, kind of think of our I, j, and k in 3 dimensions, our standard basis vectors. We use the fact that those are orthogonal to each other all the time without even realizing it. And we'll see that we can actually work with a similar thing in any vector space, any inner product space, and actually make use of some of those same ideas to make things really nice. So, leave that for now. We'll talk about that next week. So, see you later.